Good afternoon. And while we've been hearing about such exciting stuff as cloud, I'm here to depress you all and talk about the state of storage benchmarking. Benjamin Disraeli once said there are three kinds of lies: damn lies, and statistics. And this, of course, applies even more to storage benchmarking, where everything any vendor does is a lie, almost by definition. So the subtitle of my presentation is How Storage Benchmarks Are Broken and What We're Doing to Fix Them. So just a second, I've been around a while. I'm one of the influencers. I now run a test lab where we do things like demonstrate that scale-out storage continues to operate after you destroy one node with about 4 pounds of thermite. I do a podcast with my compatriot Ray Lucchese called Graybeards on Storage, and being the fool that I am, I've decided to take on the problem of the fact that all of our benchmarks are broken. So, not realizing this was a shorter presentation, I've created an agenda, but we don't really need it. The main point is that I've been in writing saying that all of our benchmarks are broken since 2011. I actually found a tweet of mine from 2008 that essentially said the same thing. The problem is multifaceted. The first problem is that we have many bad benchmarks and not many good ones. Most of what you see in terms of published benchmarks or instructions from vendors about how to run a POC fail at one end of the spectrum or the other. They either tell you, run this micro benchmark that does 4K, 100% random, and that's going to behave like your Oracle database. Or they say, run your actual application and test the storage system because nothing else will work. But they forget that applications don't generate storage traffic unless there are users pounding on keyboards telling that application to do something. So in the 30 years I spent as a consultant, I had one client who had the automation scripts and the framework to use their production ERP application and test the storage system. That was a project that I did while I was with Deloitte & Touche, and I happened to know the line item on our proposal for that was $720,000 to generate the scripting. So the truth is, customers just can't test with their own applications. And so we have the overly simple micro benchmarks. We have the inaccessible benchmarks like SPC-I. SPC is a vendor-driven consortium that exists so that vendors can generate hero numbers. It is all about bragging rights. Very rarely are the systems that are tested by vendors in SPC systems that any customer has ever bought or has ever dreamt about buying. And since you can't run SPC, all a benchmark like SPC is good for is comparing whether the tuned within an inch of its life Vmax is as fast as the tuned within an inch of its life FAS. But it tells you nothing about what's going to happen in your environment. Even worse, the SPC guys have promised me personally every year for the past 5 years that next year SPC will be capable of running on a system that does data deduplication. Right? SPC is a type of benchmark that's based on a trace, where some customer many, many moons ago recorded all of the sizes and locations of all the IOs that their ERP system did. And SPC plays that back. But when they play it back, they write a fixed data pattern to the storage system. So if you have data deduplication, it all deduplicates to one block and the performance numbers are meaningless. Not to mention that DataCore specifically decided to see just how fast they could make SPC run by putting the performance generator and the storage system all in one maxed out DL380 and saying, look, we got 1 billion IOPS out of this thing but it has no fault tolerance at all, not even RAID, which of course is not the kind of environment somebody would run OLTP, which SPC is designed for. So the benchmark you see published most often is 8 KIOs, 60/40 read-write, 100% random. And that benchmark is approximately 7% accurate to the OLTP application that it's pretending to emulate. It's not, 8K isn't even the right I/O size. If you look at the graphs in the lower left, let's see, there's a laser on here. So this is what all of Nimble's customers running Oracle for the volumes running Oracle report. And this is what all of Nimble's customers for SQL Server running SQL Server report. And only 33% of the IOs are actually 8K. And less than 6% of the data that's written is actually 8K, because these graphs are by number of IO. This is the same data by bytes. Since one 64K IO is 8 times as much data as one 8K IO, it all shifts very rapidly to the large IO size. The folks at Pure have started saying, well, the truth is the average IO size is really 32K. But the truth is it's not about averages. If you look at applications, you very frequently see there are a couple of peaks. And a storage system that does, an application that does a lot of 4K and a lot of 64K averages to 32K, but whether the system does 32K IOs tells you nothing about how well it's going to deal with that application. The real problem is that storage systems have advanced. The reason we use the 4K or 8K 100% random is because in the 20th century, when storage systems used disks alone, that was the worst case because a very small amount of DRAM as a cache would be fooled by it being 100% random. Disk drives seek a lot. Random is the worst thing you can do. As soon as we introduced flash into the market, 100% random no longer was worst case, and since it's not worst case and it's not representative of any real application, essentially it's meaningless. What we need are applications that both act like real applications in terms of how they would behave in a multi-tiered storage system and how they would behave if that multi-tiered storage system did data reduction. And all of this gives vendors the opportunity to lie to you. Right? The first lie is we do 1 million IOPS, and we don't tell you what the latency is. And this one is actually more a problem from some of the websites than it is from some of the vendors. There are a group of websites, perhaps the one that you guys see most often is Storage Review, where the guys doing the testing never worked in an enterprise data center. And so they're testing enterprise storage systems as if they were testing individual disk drives or individual SSDs. And they will report, well, when we put a queue depth of 400, we got 5,000 IOPS from this product. But if you look at the curve, that 5,000 IOPS is at like 4 seconds latency. And your applications would have fallen over and died long before you reach that number. So anytime you see IOPS, it's important to see latency. The other common lie is to run the test at 100% 4K random reads and leave the writes out on a flash-based system. Flash is inherently faster at doing reads than at doing writes, and so now we're saying if you ran this completely fictional application, you would get this completely fictional data. The most common problem is running a benchmark where the total data set size is too small. If you have a hybrid array that has 10% of its capacity in flash, and you want to know how that's going to work supporting your large mix of VMs that are going to occupy 70% of its total space, running a small test that fits entirely in the flash layer tells you nothing about how well this system behaves when you miss. And having tested many hybrid systems, the behavior you should be most interested in is not how well does it perform when delivering data exclusively from the flash, but how steep is the cliff as I start exceeding the flash capacity. Does my performance fall off on a nice gentle curve, or do I go from 1 millisecond latency to 20 milliseconds latency as soon as I hit that cliff? Vendors, especially Nutanix, will say, well, your working set should fit in flash. Working set is inherently a lie, simply the words, because nobody ever specifies the time domain of that working set. I used to write a daily backup and disaster recovery column for Information Week. As a backup guy, working set is every file that got touched today that's going to be in my incremental backup. As a database administrator, my working set is every record of the database that got accessed in some period of time. And is that a 10-minute working set, or a 1-hour working set, or a 1-day working set? And then they say, oh, working set is the whole database. And that just means that I'm paying for the flash and I'm buying the spinning disk that I'm not going to use, so why did I buy it in the first place? This is as true when we're dealing with application level benchmarks as it is when we're dealing with storage level benchmarks. So application level benchmarks like TPC-C or HammerDB or Dell's Benchmark Factory in the disk era were substantially more accurate than pure synthetic benchmarks because they had the overhead of the database server involved, and at least the database server's pattern of accessing the disk was similar. But if you run those tests with a small enough database, very interesting things occurred. I was writing a blog post where I wanted to show what the I/O pattern of TPC-C was. And because this involves creating a storage trace and basically some big data analytics on that storage trace, because the trace has one record in a CSV for every I/O, and so 1,000 IOPS for an hour is 3.6 million records, and I was running like 10,000 IOPS for an hour, so it's 36 million records. And to make the analysis simpler, I said I'm going to use a small database, so at least the range of LBAs that I have to be concerned about is small. Well, it turns out that if you use a SQL server with 6 gigabytes of memory, because it's VMware and why create a SQL server with less than 6 gigabytes of memory, about 5 minutes into the run, the whole database has loaded into the SQL server's cache, and 100% of the I/O being seen at the storage system is writes. And the database engine reports that it's doing 400,000 transactions per minute. And the storage system reports it's doing 2,000 IOPS because it's not handling any of the reads, it's just doing the writes. So it's very easy to fool those systems into giving you very nice publishable numbers that no end user will ever see. So I got frustrated. After 7 years of complaining about this, I decided that I'm just going to solve the problem. And I created a new consortium that I'm calling the Other Operation, which the Monty Python fans in the room will recognize, and got together a group of like-minded vendors to fund the project, and then went out to see just how applications and storage actually interact. And I decided that there were 6 dimensions or 6 axes on which we needed to understand how an application interacted with storage before we could build a benchmark that emulated that application. And so we needed to know what the read-write mix was, and frankly, doing 8K 100% random I/O gets the read-write mix about right. Real OLTP is about 60-40. Then we needed to get the I/O size mix right, and it's not very accurate in that dimension. And those two pieces of data we've been talking about for a long time, and the data is readily available. Nimble collects a lot of that data in InfoSight, and many of the other vendors have started collecting similar analytics. Things get more complicated when we start talking about distributing I/O across the disk, and I'm going to say disk meaning a logical volume that could be flash, but I'm an old storage guy, so it's a disk. But how the I/Os are distributed across the disk. Because if you have this hybrid system and the I/Os are very concentrated, that application is going to run very well on a hybrid system. If it's got one large hotspot that stays put, that data will end up in flash and you'll get great performance. If you've got another application that creates 20 little hotspots and they move around, well, how that application is going to perform on a hybrid system depends on what the page size for the hybrid system is. Some hybrid systems promote and demote data in 4K blocks. Some other ones promote and demote data in 1 gigabyte blocks. And so if you have 20 small hotspots and 10 gigabytes of flash, the system that's moving data a whole gigabyte isn't going to get all the hotspots into the flash. The one that's moving them in 4K is. So we need some detailed data about how I/Os fall on the disk so that we can make the benchmark do the same thing and display that this system that does 4K movement performs way better than this system that does 1 gigabyte. What we've been traditionally done is just talk about adjacency or sequentiality. Was this I/O sequential? Well, that matters in a spinning disk system. It doesn't really matter in a hybrid. The other problem is that we don't really know anything about compressibility and deduplicatability. If you have a hybrid system that does data compression and/or deduplication, the effective size of the performance layer is increased by however much the data reduces, because you can fit more data in the performance layer and have a higher hit ratio. We don't know how these applications compress and dedupe. What we know qualitatively, if you ask anybody in the storage industry, you say, I want to have a storage system for Oracle databases, how much is it going to compress and dedupe? The answer is, it's going to compress pretty well and it's not going to dedupe much at all. But we don't have any numerical data. We just have gut feels for these things. And then the last factor is, how does this change over time? What's the temporal change? So we all know, kind of instinctively, that the database drive for an OLTP application looks something like this. So this is a stacked bar by I/O size, and it's the LBA arranged across the bottom, and this is where all the sales orders for 2012 are still in the database. We're not accessing that part of the database at all because those sales orders are long satisfied. The log volume looks like this. It just does sequential 64K writes. But we test it with a pattern that looks like this. And that, of course, doesn't do anything to properly test the system. Like John Snow, we know nothing about how the application and the storage system actually interact. And this is the problem I found myself in about 3 months ago when I finally figured out how to make a workload generator pretend to be a real application. I then set out to look for public data about the spatial distribution of I/Os for real applications, and there is none. Well, there is some. SNIA has 12 traces and Microsoft has 4, and the newest one of them is from 2008, so they're probably applications nobody runs anymore. So, as I said, read and write size and I/O as data is available. Reducibility and spatial data isn't. And so the first step in developing a new set of benchmarks is asking you, the community, for help, to help us understand how applications and storage interact. And we've got two pieces of data that we're looking for. The first is we've made a reduction scanner that you can point at your data. All right, let me rephrase that. You can point at a restored backup of your data. And it will create a report that tells us how compressible and deduplicatable this data is. And it is a human-readable report, so you can look at it and make sure that you understand exactly what data you're sending us, which is this data compresses, and there's like 12 numbers that describe how well it compresses with different algorithms, and then this data deduplicates. There's about 4 pages of numbers that describe how it deduplicates, but you're not sending us any personally identifiable information, and we want to make it very clear that you can tell you're not sending us any personally identifiable information. The other piece of data we need is a trace. The easiest way to generate a trace is if you run vSphere, and I hope some of you do. There's a built-in facility called vSCSI stats that will generate a trace file. Again, it's a human-readable CSV, and all it says is, at this time, at this LBA, an I/O of this size that was a read occurred. Doesn't tell us anything about the contents. But from that, we can generate the spatial I/O heat map so that we can create hotspots like real applications. We're in the process of creating a public repository where you upload these files to us, we do analysis on them, and we say this application probably compresses very well, it creates a small number of large hotspots or a large number of small hotspots. We create those stacked bar histograms so that you can have a better idea how your applications work, and so that eventually the academic community and the rest of the industry can look at the repository and see the information about how applications work, which might, in the best of all possible worlds, mean vendors can create better storage systems for us. The end result from the other operation is tools for you as an end user organization to do a proper POC on a storage system. So we're looking to create, hopefully, 8 high fidelity. And what I mean by high fidelity is approximately 70% accuracy to the real application, which is only 2 orders of magnitude better than we are today, for about 8 applications. You as an end user buy the cookbook for $9.95 in dollars. That gives you all the load generators and 2 OVFs, the manager and the load generator. You start the manager OVF, and it says, here are the 8 workloads. What percentage of the storage load in your data center comes from OLTP or email or the various applications? And it spawns sufficient VMs to run that mix of workloads against the system you're trying to test, and reports back the performance of that system. Rather than chase latency by pushing the queue depth as deep as we can, for each class of storage system, we have a target latency. So if you're testing an all-flash array, we increase the amount of work the systems are doing until latency reaches 1 millisecond. Because if you have an all-flash array, you have it because you want low latency. For a hybrid array, it's 5 milliseconds. For an all-disk array, it's 20 milliseconds. and we report how many IOPS you can deliver at that latency, and graphs that show all sorts of other interesting things like how variable the latency is, how consistent. And then we actually take a step back and we say, now let's look at this system the way you're actually going to use it in a data center. We're going to dial the VMs back so that we're generating 70% of the total IOPS the system can do. And we're going to run that, and as time goes on, we're going to vary how much I/O is demanded by the various VMs in the test so we can see how reactive the system is. Right? Now that we're in the hybrid era, there's a big difference between the system that does caching that reacts right away and the system like an old VMAX that does sub-LUN tiering once a day. If your application mix changes over time, we should see how well that storage system delivers it. At some point during this 2-day test, and now log into the storage system and create a snapshot. And let's see what the performance impact of the snapshot is. So the cookbook walks you through the process, not just of generating the hero number to see how fast the thing is, but to see how well it's going to perform in a much more real-world environment. And of course, because I've spent 20 years gaming benchmarks to write reports for clients, the rules about how you can game the system will be very strict because I am a sneaky kind of guy and it's going to have to be something I can't think of. So if iometer is 7% accurate, our goal is to be 70% accurate. What we know we won't be able to do is have the load of an individual workload change substantially, but one step at a time. Which brings me to the end of my prepared presentation. Thank you, folks. Any questions? Any volunteers? Even more importantly.
What's your view on load dynamics as a solution? Although that's like a company who makes money.
Load dynamics makes a great product. But load dynamics product starts at about $100,000 and requires, I've had it in the lab. I know the guys at Load Dynamics. It requires 2 months to learn how to work a load dynamics box. They sell it for $100,000. But the idea is for this all to be much more accessible than that. Right? The workloads themselves are going to be open source and available on GitHub. The $9.95 for the cookbook is to get the simplicity of the OVFs and the instructions and email support, not the benchmarks themselves, which we're making freely available. We're really aiming for a solution for people who can't afford load dynamics. Yes, Nigel?
So how important is it to have multiple servers accessing your storage over multiple paths and things like that?
It's all very important. And so in it, when you fire up the management machine, in addition to what's the load from your various VMs, we have to ask, what's the total size? What's the size of the performance layer versus the capacity layer? And how many ports does it have? Because as far as I'm concerned, if we're talking about a host to support VMs, then you need to generate at least as many VMs as there are ports so that we can actually, when you start talking about a scale-out system, SolidFire, for example. Is Gabe still here? No, Gabe left. But SolidFire, for example, is really good at running a large number of workloads. It's not so good at running one huge honking Oracle server. And so we are looking to investigate that as well.
So how are you going to simulate mixed workloads, where you've got your mail server, you've got your database server, you've got God knows what running all on a single array? So
right. We're going to spin up multiple VMs.
Yeah, because that's one of the things we find with a lot of the benchmarks. We're very tuned for a single workload.
Yeah, benchmarks today are designed to generate that hero number. And so you can say, this is how well it handles SPC. But that's not how we buy storage today. And so, when you fire the system up and you say how big the system is and what class it is, there are built-in decisions about, oh, this is an all-flash array that's 500 terabytes. It will be able to handle, it probably will be able to handle 1 million IOPS. Let me spawn as many VMs as I need to generate 1 million IOPS.
More questions?
All right. Thank you, folks.